Hi guys, I'm from Math Academia, and today let's look at a question on vectors. The question states that the picture shows a concrete sculpture in Rotterdam, Netherlands, made of 3 identical square slabs of side 8 meters. The 3 slabs are assembled perpendicular to each other such that they meet at one common point O. Each slab has one vertex fixed to the horizontal ground, represented by the plane pi, and one vertex fixed to the center of another slab. The slab PA is part of plane x equals to 0. It has one vertex point A on pi and another vertex on the center of PC. The slab B is part of the plane y equals to 0, where it has one vertex point B on pi and another vertex on the center of PA. The remaining 2 vertices are denoted as point D and point E. And the slab PC is part of the plane Z equals to 0. It has one vertex point C on pi and another vertex on the center of PB. Point 0 is taken as the origin, and perpendicular unit vectors I, J, and K are defined as shown in the diagram, with I, J, and K along the edge of PC, PA, and PB. For the first part, they want us to show the Cartesian equation of pi. Alright, let me expand the diagram so that we would be able to annotate the diagram clearer. So firstly, let's extend I, J, K to get the x, y, and z axis. So if I were to extend I would have the x-axis, and if I were to extend J along the plane PC, I would have the y-axis, and if I were to extend K, I would have the z-axis. Alright, so PC, the plane PC, is lying in the xy axis. So for plane PC, we have z equals to 0. Alright? And for plane B, it lies along the zx axis. So for plane B, we have y equals to 0. And for plane PA, it lies along the yz axis. So for plane PA, we have x equals to 0. Okay, so to find the plane pi, we need to find the coordinates of A, B, and C first. So let's look at point C first. Okay, so for point C, it is on the PC plane. So remember, just now we said that PC plane has z equals to 0. Therefore, for point C, we know that z equals to 0. Next, let's look at the coordinates of x. For point C, it would move 4 units in the positive x-axis, as the origin lies along the middle of the plane PC. Okay, so 4 units up the positive x-axis, so we have x equals to 4. And it moves 8 units in the positive y-axis. So therefore, we have y equals to 8. Therefore, the coordinates of C would be denoted as 4, 8, 0. Okay. Next, let's look at point B. Okay. So we move 8 units in the positive x-axis, and we move 4 units in the negative z-axis. Alright, and remember, because point B lies on the plane PB, y equals to 0. So for point B, x equals to 8, y equals to 0, and z equals to -4. Therefore, the coordinates of point B would be 8, 0, -4. Alright, lastly, let's look at point A. Alright, So for point A, I'll use green to denote it. We move 4 units in the positive y-axis. Okay. And we move 8 units downwards in the negative z-axis. Okay, so therefore for point A, as point A lies along the plane PA, x equals to 0, y equals to 4, and z equals to negative 8. Therefore, for point A, the coordinates would be 0, 4, negative 8. Okay, now we have the position vector of A, B, and C. Plane pi contains the points A, B, and C. So we need to find AC and AB, and then use cross product rule to find the normal of plane pi. So let's try and find the equation of vector AB. Vector AB would be given by position vector of B minus position vector of A. Previously, we have found the coordinates of OB and OA. I would just bring the values in. I have 8, 0, negative 4 minus 0, 4, negative 8. So vector AB would give me 8, negative 4, and positive 4. I would bring out the common factor of 4. I'll have 4, 2, negative 1, and 1. Next, let's find the vector AC. So to find vector AC, I would take the position vector of C minus the position vector of A. So if I bring in the values that I have got previously, I would have 4, 8, 0 minus 0, 4, negative 8. And that would give me 4, 4, and 8. All right. I will bring out my common factor of 4. I would have 4, 1, 1, and 2. Okay, now knowing the vectors AB and AC, we can use the cross product to find the normal vector. All right, let me erase my working so I have more space. So let's cross AB and AC to find the normal vector. So AB cross AC. Okay. I can use the unit vector 2, negative 1, and 1, and 1, 1, and 2 instead of having a more complicated vector. All right. So if I take 2, negative 1, and 1 cross with 1, 1, and 2, I would have negative 1 times 2 minus 1 times 1, and negative 2 times 2 minus 1 times 1, 2 times 1 minus negative 1 times 1, which simplifies and gives me negative 3, negative 3, 3. If I factorize out my common factor of negative 3, I'll be left with 1, 1, and negative 1. Okay, so therefore, the normal of plane pi is 1, 1, and negative 1. In order to find the equation of plane pi, I can use any of the coordinates of point A, B, and C as they all lie on plane pi. I would take the position vector of A. So I have R multiplied by normal, which is 1, 1, and negative 1, equals to the position vector OA, which is 0, 4, negative 8, multiplied by 1, 1, and negative 1, which gives me 12. Okay, so therefore, I would derive the Cartesian equation of pi as x plus y minus z equals to 12. Okay, this would be my answer for part 1, and I have shown that the Cartesian equation of pi is x plus y minus z equals to 12. Okay. The next part of the question wants us to find the position vector of f if we were to construct a vertical support from O to point F on pi. such that OF is perpendicular to pi. So to find the foot of perpendicular F from O to plane pi, I know that the position vector OF is perpendicular to plane pi. And I know that OF, since OF is perpendicular to plane pi, OF is parallel to the normal. So OF can be represented by lambda n, right? Where n is the normal. So lambda 1, 1, and negative 1. If I bring my lambda in, I would have my position vector F to be represented by lambda, lambda, negative lambda. As F lies on plane pi, my position vector OF also satisfies the equation of plane pi, which is x plus y minus z equals to 12. So if I were to bring the coordinates of OF into my equation of plane pi, I would have lambda plus lambda minus negative lambda equals to 12. So this simplifies into 3 lambda equals to 12. Therefore, lambda equals to 4. Okay. Therefore, the position vector OF is given by 4, 4, and negative 4. And that would be my answer for part 2. Alright, let's move on to the next part of the question. Next part of the question states that a pigeon is at points P with coordinates 2, 11, and 1. It flies in a straight line and rests on the sculpture along the edge of DE. Given that the pigeon rests at the point nearest of P, find the coordinates of this point, and hence find the distance the pigeon flew. So essentially, what this question is asking us to find is to find the foot of perpendicular from P to line DE. So if I were to sketch a rough diagram over here, I will have the line DE, okay, and point P would be around here. I need to find the position vector of this. So first, let's figure out the coordinates of D and E. To find coordinates of point D, I move in the positive z-axis by 4 units, and I move in the positive x-axis in 8 units. So that D would have x equals to 8, y equals to 0, and z equals to 4. Okay, for the coordinates of point E, I just move in the positive z-axis by 4 units. So therefore, for point E, x equals to 0, y equals to 0, and z equals to 4. Okay, now knowing the position vector of D and E, we would be able to find line DE. Line DE is given by the position vector of OE minus the position vector of D. Okay, so I have 0, 0, 4 minus 8, 0, 4, and that will give me negative 8, 0, 0. Alright, I bring out my common factor of negative 8. I would have 1, 0, 0. The equation of line DE can be represented by any point on line DE. So I would take the position vector of D, which is 8, 0, 4, plus the direction vector of DE, which is 1, 0, 0. Let Q be the foot of perpendicular. So we know that point Q lies along line DE. Therefore, the position vector OQ can be represented by 804 plus pi times the direction vector 100. So if I were to bring in my lambda and simplify my vector, I would have 8 plus lambda 0, 4, where lambda is a value to be found. Vector PQ can be given by position vector OQ minus the position vector OP. Position vector OP is actually given to us in the question, which is 2, 11, 1. And OQ is what we have derived before. Alright, so I'll bring in all of my values. I have 8 plus lambda 0, 4 minus 2, 11, 1. So this simplifies to 6 plus lambda minus 11 and 3. And since DE is perpendicular to PQ, the dot product of DE and PQ should give me 0. So I should have 6 plus lambda negative 11, 3 dot direction vector 1, 0, 0. This should give me 0. Okay, so from here I would derive that 6 plus lambda equals to 0. Therefore, lambda equals to negative 6. Alright, let me erase my previous working. So now I have found my value of lambda. I would be able to find the coordinates of Q. So coordinates of Q would be when I substitute lambda equals to negative 6. So position vector OQ would be 8 minus 6, 0, 4, which is 2, 0, 4. Since they are asking for the coordinates of Q is 2, 0, 4. Alright, and they want us to find the distance the pigeon flew. So we would find the modulus of PQ, which is the modulus of 0, negative 11, and 3. Okay, which would give us square root of 11 squared plus 3 squared, which gives me square root of 130. So therefore, the distance the pigeon flew would be 130. Alright. The next part of the question states that another pigeon has flight path with equation x minus 1 over 3 equals to 2 minus 1 over 4 equals to z plus 3. Alright, without using a calculator, they want us to determine if the flight path of two pigeons cross. Okay, so first we need to find the equation of path for two pigeons. So for pigeon 1, in the previous part we have concluded that PQ is 0, negative 11, and 3. So if I were to take a point that lies along the line PQ, the equation of line PQ can be represented by 2, 11, 1 plus lambda 0, negative 11, 3, which can be simplified to 2, 11 minus 11 lambda, 1 plus 3 lambda. Alright, and for the second pigeon, so we would let x minus 1 over 3 equals to 2 minus y over 4 equals to z plus 3 to be represented in mu. Okay, so from this equation, I can represent x, y, and z in terms of mu. So x would equal to 1 plus 3 mu, y equals to 2 minus 4 mu, and z equals to negative 3 plus mu. Alright, the flight path of the second pigeon can be represented by r equals to 1 plus 3 mu, 2 minus 4 mu, and negative 3 plus mu. Okay. So equating the two equations that we have that represents the flight path of pigeon 1 and pigeon 2, we have three equations. Alright, equating x with x, I have 2 equals to 1 plus 3 mu. This would be my first equation. My second equation would be 11 minus 11 lambda equals to 2 minus 4 mu. This would be my second equation. And my third equation would be 1 plus 3 lambda equals to negative 3 plus mu. This would be my third equation. I have three equations and two unknowns. So first, let me use the first two equations to find the value of lambda and mu. Okay, using my first two equations, I would have mu equals to 1 over 3, and substituting mu equals to 1 over 3 in my second equation, I would have lambda equals to 31 over 33. So using these two values of my mu and lambda, I will substitute them into my third equation. Using my third equation, I have 3 lambda minus mu equals to -4. Okay, substituting my values of lambda and mu into the equation, I have 3 multiplied by 31 over 33 minus 1 over 3, and I realize that this does not equal to -4. So therefore, I can conclude that the two flight paths do not cross. Alright, and that will be my answer for part 4. Alright, I hope you understand my explanation. It has been a very long explanation, and I hope that you enjoyed yourself. Thank you, and I'll see you again. Bye!